Guys, back again, even more vector calculus. Before I forget, I want to just encourage you to look at the Khan Academy resource that I've put a link to it on Loop. So I want you to look at that if you could, please. There's some very nice notes, background to this stuff, and there's some, in particular, some quizzes which you should take. There's some stuff on partial differentiation which you probably did with man, so you might want to look back on that and see, make sure you can do that, because you need partial differentiation for the stuff we do. So as I said, there's some very, very nice quizzes. The directional derivatives quiz, though, you might just not look at it because he does it in a different way. He doesn't do it correctly, actually. But the rest of it is pretty good, and there's some very, very interesting notes if you have time. But particular, there are all these practice quizzes that you should definitely take because you're working on your own and you need to check to see if you're actually making progress. And this is the easiest way to make progress. Okay, so I want to just continue on what we've been doing. We were looking at the gradient operator. And here is the gradient operator, and you can, once you have this definition, you can start playing around with it and start proving some nice theorems and start doing some nice little mathematics, applied mathematics. When I was your age, you might find this hard to believe, but I had very few friends, and I used to love this stuff. I thought this was amazing, because you can sit down and actually prove things. And I know you're engineers and you're not into proofs, but from a logic point of view, this is amazing. You can sit down and show that something makes sense, as opposed to a lot of engineering, which is, this is for me looking in from the outside. A lot of engineering is wave your hands and, we all know this kind of stuff. It's like physics sometimes, whereas mathematics is much cleaner. Okay, so I just want to show you how you can just use this definition. Remember what f is a scalar field, so it's a function of x, y, and z, and time as well. But when you're talking about the gradient operator, you only use the x, y, and z coordinates. Now, f can be anything, folks. You could replace it. No matter what f is, this is the definition. So if f was sheep, the gradient of sheep is delta sheep delta x along I plus delta sheep delta y along j plus delta sheep delta z along k. That is the basic idea. Whatever you're getting the gradient of, you plug it in to the right-hand side. And that's what makes these theorems so easy to prove, actually. So we're going to prove a theorem for the gradient, but you can also use these proof theorems involving the divergence and the curl, which we haven't done yet, but we will do in the next lecture. And you can use all these three operators to get some nice results. But I'm just going to just show you I'll show you how to do one. Okay, so suppose f is a scalar field, then you can prove that the gradient of f to the power of n is n f to the power of n minus 1 by the gradient of f. And this is basically the chain rule for the gradient operator. So whatever f is, if you've got a power, you just differentiate the power first, and then you differentiate inside the power. And and this makes calculations very, very simple, as I will illustrate in a second now. So don't be put off by the complexity or the seeming complexity of what we're going to do next. It's not that difficult, because at the root of the calculation is this very simple theorem. But before we can use it, we have to prove it, because we can't, if I just wrote this down, maybe it's not true. So the first thing I want to do is I want to prove that this is correct. So here's the proof. Now, the first thing you do is, on the left-hand side, you have the gradient of f to the power of n. Okay? So what you do then is you go to the basic definition for the gradient of f and replace f by f to the power of n, because that's what you do. Remember, the gradient of sheep is just delta sheep delta x along I, etc. Okay? So now what you do is each of these individual terms you differentiate. And this is the chain rule. So if we use the chain rule with man for partial differentiation, if you want to differentiate f to the power of n with respect to x, you differentiate the power first, and then you differentiate f with respect to n. You differentiate f with respect to x. And that gives you the first term. Similarly for the y term, and similarly for the z term. And this is what you get. So if you look at, we say the first term there, delta f to the power of n delta x. You differentiate the power, so you get n f to the power of n minus 1, and then you differentiate inside the power and you get delta f delta x. And similarly for the y and the z terms. Now you will see in the second line here, there is an n f to the power of n minus 1 term common, so you can bring that outside like this. And then what's inside brackets, folks, is miraculously the gradient of f. That's exactly what the gradient of f is. So you've proved the result. Okay, so QED. So when I was in school, this was beaten into me. You had to put in QED at the end of every result that you proved. Quod erat demonstrandum. Yeah, so classical scholar as well as a mathematician. Yeah, I'm everything. So so that's the result. That's the proof. And I think it's and you can do this. And it all just comes from the definition of the gradient of f. And as I say, I'm just doing it because it's some nice applied mathematics, and I like it. I used to like it. I still like it. I think it's something very elegant about this. Okay, there you are. Okay, so I'm just going to apply that theorem now to a seemingly very difficult problem. All right, and it's not that difficult actually once you just trust in the rules. So I want to get the gradient of 1 over r, where r is the mess there on the left hand side. It's the square root of x minus x naught to be squared plus y minus y naught to be squared plus z minus z naught to be squared. And I'm going to use the chain rule theorem to calculate this. If you don't use the chain rule theorem, and you don't have to, it does get complicated. So the chain rule makes things a lot simpler. So here's the solution. The first thing you do is you rewrite what you want to get the gradient of as a power. So 1 over r is 1 over the square root of what's inside, and 1 over the square root of something is just that something to the power of minus a half. Okay, that's important. So all I'm doing is I'm rewriting the gradient of 1 over r as a power, because when I write it as a power, I can then use the theorem, the previous theorem, that theorem, to actually, that theorem to calculate my answer. Sorry guys, I have to go back and do it again. Sorry. So what I'm going to do now is I'm going to use the theorem to get the gradient of 1 over r. So what I do now, folks, here is before I just want to show you let's talk about what you have to do. What you have to do here now is you differentiate the power first, and then you differentiate inside the brackets. So you differentiate outside the brackets first and then inside, and multiply. So when you differentiate something to the power of minus a half, you get minus a half times the something, and then you must subtract 1 from the power. So you get minus 3 over 2. And then you must differentiate inside the brackets using the chain rule. And that's what you get. So minus a half comes from the fact that I'm getting the gradient of something to the power of minus a half. So I differentiate the power first, and then I get the gradient of what's inside the power. And in that case, it's x minus x naught to be squared plus y minus y naught to be squared plus z minus z naught to be squared. And remember how you get the gradient, folks. You differentiate respect to x, you put that along I, you differentiate respect to y, you differentiate respect to z, and put those along j and k respectively. And in this case, it's very easy to differentiate respect to x, because you've got 3 terms here. Only one term depends on x, so you only differentiate one term. Okay, so you get 2x minus x naught when you differentiate respect to x. So that's what you get. So you get 2x minus x naught along I, you get 2y minus y naught along j, plus 2z minus z naught along k, and that's your answer. Now you can pretty this up a bit. You can put a little bit of, you can make a bit of effort here to look nice, if you wanted to. You can leave it like this, folks. You walk away, that's the answer. But you'll see here, guys, there's a half here on the left-hand side. And there's a factor of 2 when you do the gradient. So you can cancel the 2's, okay? And then you realize maybe that on the power of the x minus x naught to be squared plus y minus y naught to be squared plus z minus z naught to be squared to the power of minus 3 over 2, you can write that as 1 over r cubed, because r is the square root of x minus x naught to be squared plus y minus z minus z naught to be squared. So you can pretty that up if you wanted to. All right, so you get a very nice little result. Okay. Now, again, guys, I do appreciate that this is kind of engineering and mathematics for engineering mathematics' sake. For the Really, that's what it is. Certainly, when you start working for Intel, you're not going to be using the gradient operator in this way. But it's nice mathematics, and you might see this in other courses, and that's the reason why we're doing it. In particular, those of you who are doing electronics will see this in electromagnetism. But the mechanical guys might see it as well in fluid mechanics as well. So there you are. That's what you do. Just a little bit of terminology, guys, because you might come across this in your courses. You may wonder what's going on, but there is a little bit of terminology. If you obtain a vector using the gradient of a scalar field f, then that vector is called a conservative vector, and that's a very important quantity in applied mathematics and engineering analysis and in physics. And what you take the gradient of is called the potential. And again, that is a very important little just terminology. And the reason why I'm giving it to you guys is because when I did this the first time, people were throwing these terms about really without explanation. And so I want you to give, and usually, as I said to you before in the first lecture, when you actually start looking at what these terms mean, they don't mean that much. And actually, they're not even essential to your understanding of this stuff, but it's just stupid terminology. So if you get a vector from the gradient, for using the gradient operator, that vector is called a conservative field, and what you get the gradient of is called its potential. And so there's a kind of a link between the two things. All right. Okay. Now I'm just going to show you one application of the gradient operator. Now we've already seen actually in the first lecture the most important application of the gradient operator is its rate of change. It calculates rate of change. And in particular, remember, we did this kind of directional derivative stuff. That's important. But the gradient operator gives you the magnitude of the gradient operator gives you the greatest rate of change, and the gradient operator divided by its magnitude gives you the direction of the greatest rate of change. So that's the most important application of it. But there are loads of other applications. I'm just going to give you one here. Now, if I ask you this in the exam, I would give you exactly what it is. I would tell you what we're doing, and I will tell you how the gradient operator is involved in the question. Now, here's an example. I think this is amazing because it's just there's something very, very simple about it. You've got a surface, a two-dimensional surface in three-dimensional space, and it's represented in the diagram there. It's called S for surface, haha. And at each point on the surface, you have a normal, which is perpendicular to the surface. Actually, you've got two normals at each point. There's one normal pointing as you see it, but there's another normal underneath the surface pointing inwards. So you've got an outward normal and you've got an inward normal. But I've just illustrated, because you can't see the inward normal here, I've just shown you the outward normal. And usually it's called n for normal, the normal vector. Okay? But how you calculate the vector, or how you calculate the normal, is very, very easy. Every surface in three-dimensional space can be represented using the equation f of x, y, z is equal to c. And all you do then is you get the gradient of f. That's it. That's all you do. Okay, so let me just give you an example and show you an example. Now, this looks complicated, and it's not complicated at all. And yet there's all this nonsensical terminology, which you can just forget about. It says, find the two unit normals, which is fine, to the cone of revolution. Now, that's all nonsense. The cone of revolution, you don't care what it is. What you have there, folks, is you have a surface. And it's defined mathematically by z squared is equal to 4x squared plus y squared. And you're interested in the normals to that surface at the point 1, 0, 2. Okay, that's it. So what you have to remember now is that if I want to get a normal to a surface, I must get the gradient of the equation of the surface. So what I do is I rewrite the equation of the surface exactly in the form that I need. So what I need is I need all the x and y's and z's on one side, and I want all the constants on the other. And in this case, the constant is equal to 0. So what I do is I bring the 4x squared plus y squared over to the other side, and what I'm left with then is z squared minus 4x squared plus y squared is equal to 0. And then all I do, folks, is I forget about the equals to 0 bit, and all I do then is I get the gradient of z squared minus 4x squared plus y squared, because I know that gives me the normal, because I told you that it does. So when I get the gradient of z squared minus 4x squared plus y squared, I differentiate with respect to x, I get minus 8x along I. When I differentiate with respect to y, I get minus 8y along j. And when I differentiate with respect to z, I get 2z along k. Okay, that's it. I'm interested in the point 1, 0, 2. So x is equal to 1, y is equal to 0, and z is equal to 2. And in that case, I get minus 8i plus 4k. Now remember, guys, unit normals. I want a vector whose magnitude is 1. Minus 8i plus 4k, the magnitude of that is not equal to 1. The magnitude, in fact, is the square root of 80. And you can rewrite the square root of 80 as 4 root 5 if you want to, but you can leave it as the square root of 80 as well. The square root of, the 4 root 5 thing is for, the talented people amongst you, the electronic students. God love the mechanical people. You could leave it as the square root of 80, but electronics, because we know you're special, you might want to pretty things up for me, and you can write it as 4 root 5. But leave it as it is. Leave it as square root of 80 if you want mechanical engineers. All right. So therefore, the normals then are, you must divide minus 8i plus 4k by the magnitude, which is 4 root 5. And you put plus or minus in front of it, because remember, you can have one of the normals points out of the surface and one of the normals points in from the surface. And again, electronic students, if you want to cancel the 4s there, you would probably go on ahead and do that. And because you're talented. Okay, so you might write that as plus or minus 1 over root 5 minus 2i plus k. All right, but you can leave it like that if you want to, as it is, or you can even leave it as plus or minus 1 over the square root of 80 times minus 8i plus 4k. But whatever you want, whatever you have in yourself. And finally, guys, in this short lecture, I'm trying to keep these things down to some way manageable, because the file size is just, it's like I'm making The Godfather, part 2. The file size is just incredible when I start saving these things. So I'm trying to keep them into bite-sized chunks and hope for the best there. Again, guys, you don't care. This is just my problem, my file management problem. There's one other thing that I want to talk about before I end, and it's called the Laplacian operator. You will see this. This is a very, very important operator. You'll see this in engineering analysis all over the place, because the universe actually works. And sometimes, in particular instances, the universe works this way. The Laplacian is defined as follows. It takes a scalar field. Remember what a scalar field is, folks, is a function of x, y, z, and t. And the Laplacian operator is, it's denoted by the triangle, in this case now, squared, because that's just the notation that's been handed down to us. That's just historical artifact. So here's what you get. Now, what's important with the Laplacian, guys, is that there's no vectors involved. The Laplacian is a scalar. The gradient is a vector. Now, I do appreciate that the notation for the Laplacian and the notation for the gradient is very similar. It's just the power of 2. And there's no reason why the gradient squared should be a scalar and the gradient itself should be a vector. There's no reason. You just have to accept that these are just definitions, and you have to keep them in your brains. Okay? So the Laplacian operator of a scalar field is just delta squared f delta x squared plus delta squared f delta y squared plus delta squared f delta z squared, because that's how the universe works in many cases. Okay? F is what you're interested in, and if you get the Laplacian of f, it tells you something very, very important about the system that you're interested in. Okay, and that's the way it's defined. You will notice that there's no mixed derivatives here. It's just pure second derivative of x, second derivative of y, second derivative of z by definition. And the applications of this, and what could I ask you to do here? It's very, very straightforward. Let's look at this function here. This is just a function of two variables, x and y. So it's the natural log of x squared plus y squared. Now, guys, I'm going to have to differentiate the natural log. Remember, when I'm differentiating the natural log, it's 1 over what's inside the natural log, and then you must differentiate what's inside the brackets. Okay, so the first thing you do is you might find delta f delta x. So it's 1 over x squared plus y squared, and then you must differentiate inside the brackets and you get 2x. So you get 2x over x squared plus y squared. And then to get the second derivative, I have to use the quotient rule. So I've done it there. You get x squared plus y squared by 2 minus 2x by 2x over x squared plus y squared to be squared. And what you get then in the end is you get 2y squared minus 2x squared over x squared plus y squared to be squared. Now, if you go back up to the Laplacian operator, by definition, I also need delta squared f delta y squared. But because you've got nice symmetry here, you don't actually have to do any calculation. You know if delta squared f delta x squared is just 2y squared minus 2x squared over x squared plus y squared to be squared, you just interchange the x's and the y's. Okay, so that's what you get. So you get 2x squared minus 2y squared over x squared plus y squared to be squared. Okay, I'm saying squared too much, I know. Sorry. There is no z term here, so delta squared f delta z squared is identically 0. And when you add delta squared f delta x squared and delta squared f delta y squared, you get cancellation. You get 0. Okay, so you get the Laplacian of f is equal to 0. And the Laplacian of f equal to 0 is what's called Laplace's equation. And it describes many things in engineering systems. Many engineering systems obey that law. Now, not all do, most of them don't, but many do, and many important ones do. Okay, so this is it's an important little operator, and you will see it probably elsewhere in your course. And don't be put off by this. Okay, so it's very, very simple. It's just a definition, guys. This is what the definition is. Right, that's it. I will talk to you again